original parabola has this as a pattern. The blue one with the 0.5 out in front goes over 1 up a half, then over 1 up 3 halves, then over 1 up 5 halves. So what's happening, still have 0, 0. In grade 11, we would have talked about this being wider, because visually that's what it looks like to our eyes. The proper terminology for this, and you'll learn this now in grade 12, is that someone has taken the red graph and compressed it vertically. It's been pushed down. Because what has happened is every single y point that you had originally is now cut in half. And just like before, these numbers are all outside. Can you see that the 0.5 is not affected by the squared? So when it's not affected by the squared, we're going to say that that is outside of the function. And so that 0.5 will be a vertical compression. For the green one, with the 2, all of your y values will get multiplied by 2. So we still have 0, 0. But instead of going over 1 up 1, we're going to go over 1 up 2. Then over 1 up 6. And in grade 11, you would have said this got narrower. In grade 12, we're going to say that the graph got stretched vertically. And when things are stretched vertically, they're stretched away from the x-axis. Purple graph, same idea. Wider and going down, and the orange one, same thing, but we have the negative outside the function was what we did yesterday. That negative is a vertical reflection. So we would say that the orange graph has a vertical reflection and a vertical stretch because it is then stretched away from the x-axis. Now that's very busy on that graph. We're going to look at a couple more graphs. You can turn the page to page 194, and we'll look at these graphs separately, starting with this. Maybe. Starting with that. There. So what we're going to do is we're going to label this one as our original. And we notice on our original they've labeled a point. They've got 16, 4. That's normally not a point we label on the square root graph because it was off of our screen, but does it make sense that if you plug in 16 for x, you would get 4 for y? And then for each of these, we notice that the numbers are all outside. Outside is vertical. Outside affects the y-coordinate. And so what we're going to notice in the blue one is your y-coordinate gets multiplied by 3. And sure enough, if we label the point, we had 16, 4 on our original point, and on the blue graph, we're going to have 16, 12. And if you do the mental math, right, if I plug in 16, square root of 16 is still 4. Now it's getting multiplied by 3. So to make this a little bit shorter, here we're just going to say y by 2. Label this point 16, 8. The orange one we're going to label y by half. And finally on the purple one, So in the first set, we see if the numbers are outside the function, it's going to be vertical. We will talk about the blue and the green one being vertical stretches, because we made our y values bigger. And we will talk about the orange and the purple one as vertical compressions, because we made the y values smaller. The next one that we're going to look at, again, here is our original in red. Now the numbers are inside the function. And so the original point that they started with in red was 4,2. And anything that happens inside is going to affect the x values. And just like things moving left and right, do you remember how it was sort of opposite of what you think? For the x values, you don't multiply by 4, but you multiply by 1/4, which is the same as dividing by 4, but we'll actually find it easier to say multiplication because we'll deal with a fair bit of fractions. So whatever number you have, you're going to multiply by the reciprocal. And reciprocal in math is when you take a fraction and exchange the numerator and denominator or flip it. So I had 4 over 1, I multiply by 1 over 4. For the green one, I'm going to multiply by 1 over 2. The orange one, if I flip 1 over 2, I'm going to multiply by 2 over 1. And for the purple one, x by 4. So you'll notice that if on my original graph I had 4, 2, on my purple one, I have 16, 2, because I've multiplied my x coordinate by 4. On my orange one, I have 8, 2. My green graph has 2, 2, and my blue graph has 1, 2. So now my x values have changed, not my y values. So this is an interesting kind of, and a little bit of an abstract concept to think about. Sometimes we're going to think about the original graph and think about x values changing, and sometimes we're going to think about y values changing. I find this interesting because maybe you notice that you could actually simplify the blue one. What is the square root of 4? 2. So can you see that the blue one is the same as this? And if I changed it to that, and I'm thinking graphically, now I would have to think about the 2 as being outside the function. So for a square root graph, and this is just for a square root graph, but a 4 inside the function is the same as a 2 outside of the function. Does that make sense? And if we look at our blue graph, you see our blue graph has the point 4, 4, which would be taking my y and multiplying it by 2 to get 4, 4. So we're going to find out that sometimes in graphs, depending on how we look at it, we can view it in 2 different ways. Generally, we'll just take how it's written and start with that. So we would say that the blue and the green ones, because your x values got multiplied by a number less than 1, we would call those ones horizontal compressions. And then the orange and the purple one, because the x got multiplied by something bigger, we would call those ones horizontal stretches. Now the third one we're going to skip right now. It just does both together. The blue one, you would multiply your y by 4 and x by 1/2. Green would be y by 2, x by 1/2. Orange, y by 2, x by 2. Red one's the original, and the purple one, the y by half and the x by 2. Some notation things, personally, if you ever have y not by itself, I would always change it to the y by itself. So having that 2 with the y, I would divide both sides by 2, get a half out in front, and then notice I would have a vertical compression. Same thing on the orange one there. If I had this, I would change it to look like that. Same thing here. If you had the negative half with the y, get the y by itself. And the negative would flip it down, and then the 2 would stretch it vertically. So let's go to example 1. Here's the graph of f of x. Some of you right away will recognize the explicit equation. So sometimes you just get a random graph that they call f of x. Sometimes they give you an actual equation. This question could have been, here's the graph of the absolute value of x. And sometimes it'll be a mix of both. So this one, they just said f of x. We know that it's the absolute value x. And we want to sketch the graph of negative 1/4 f of x. And we're going to develop, as we get more and more transformations, we need to develop some techniques for doing it. And we're going to do that today. So first of all, it's always good to notice things. I have a negative, and I have a 1/4 outside of the function. Everything outside is vertical. Are you okay if I use v for vertical? Seems logical. And I'm going to use r for reflection. Perfect. That's a negative, right? A negative is a reflection. So I'm going to say that negative is a vertical reflection, and then underneath it, I'm going to write the algebra. What happens with the vertical reflection? You're going to multiply your y by a -1. Next, this is outside. It's also vertical. And I'm going to use C. What was the C for? Compression. This one we're getting it smaller. So this is a vertical compression. You would multiply y by 1/4. Now both of those are multiplying. Probably most of you will combine this later, and just with those two together, you will just write that all your y values have to get multiplied by the negative and the 1/4 together. That means they get multiplied by -1/4. So the technique that we're going to develop is going to look like this. We're going to take points on our original graph. We definitely have to take 0, 0 because it is the most important point. But then we're going to choose a couple of other points to see where they go. Sometimes there's strategy in choosing the other points. I'm going to choose 2 points that I think are strategic to choose in this question. I think 4, 4 is a strategic one. It's a good one to choose. I could choose -4 for the same reason, but I also think that -8 8 is a good one. I'm not going to tell you why they're good ones yet. After we do the question, I want you to decide if you can see why I chose those points. So those are my points on my original graph. Then at each of these points, this is going to be our technique that we're going to use. We're going to draw a mapping arrow and say, where does that point go? And above the arrow, you can rewrite, if you like, what we're told we need to do. We need to multiply our y values by -1/4. So that means all of my x values stay exactly the same. I'm going to have 0, 4, and -8. That's not going to change. But when I multiply by -1/4, well, I guess I'd still have 0, 0. But 4 multiplied by -1/4 is -1. And 8 multiplied by -1/4 is -2. So now we take those 3 new points in black, and we can label them on our graph. And this graph in particular, the textbook is testing you to see if you pay attention to details. Because I'm going to make a mistake. I'm going to make a common mistake that you might make, and you might even see, I don't see what you did wrong, Mr. JR. But I'm going to label 4 -1. I'm going to go to 4, go down 1. I'm going to label that point, and I'm going to go to -8 and -2 and label that. And what happened? That was a mistake. Sorry? It is an absolute value, but the negative, like an absolute value makes it positive, but the negative out front will flip it down, so it makes sense that they'll be negative. It goes by 2s. It's like you want to swear at the textbook just a little bit. You see, that's not nice. The graph is going by 2s. How often are you used to just counting down 1? Can you see yourself counting down 1? When you have -4, -1, but -1 is actually there, and -2. Oh, so sneaky. So check your scales. And there is our final graph. Reread the question, and we still have to state the domain and range. The domain is everything. The range of the red one was y is bigger than or equal to 0. And then on our black graph, the domain is still everything. But our range, the y values are now less than or equal to 0. Just a note off to the side, since we recognized this as the absolute value of x, another way this same question could have been asked would just be to say, graph, y equals -1/4 absolute value of x. And then from your memory, you have to pull up the red graph. Right? Because this would be one that they didn't have to give you the red graph. It was one that you already knew. So more likely, this question would show up like this. And then you'd have to say, I know absolute value of x looks like this. I know these 3 points are on that graph. -1/4 is out in front, vertical reflection, vertical compression. I'm multiplying my y values by -1/4. Now something I mentioned at the beginning. Has anybody figured out why I chose 4, 4 and -8, 8? Yeah, they divide nicely by the 4, they multiply nicely by 1/4 to get nice points. Now, It doesn't matter if you don't get a nice point. Had you chosen, like, you could have chosen 1, 1. It's not wrong, but then when you multiply your y value by 1/4, you're going to get 1, negative 1/4, which is just a little bit more awkward to try to draw than those other points. So sometimes if we can make our lives easier by thinking a little bit, that's a good thing. Because we want to try to make, this course is hard enough. If we can make it easier, that is a good thing. Okay, questions to circle on this one, just number 3.